Hi friends, myself Sanjay Gaikwad. I am working as a head and assistant professor in Department of Physics, Mahatma Phule AC College, Panvel. Today the topic is the paper number 1, Mathematical, Thermal and Statistical Physics, in which we are going to discuss on the unit number 4. This is a very interesting topic, that is the classical and quantum statistics. Generally in the statistical physics we study about the physics with the use of the statistical principles, and generally the particles are divided into two groups here: the classical statistics and quantum statistics. Classical statistics and quantum statistics, and on the basis of their properties, mean behavior or the importance, we classify the particles into different classes like classical and quantum statistics. Remember that generally physics also divided into just like classical physics and quantum physics, or you can say the modern physics. Same way here we are dividing the particles, all the particles on the basis of their properties. We divide into the two groups, that is the classical statistics and quantum statistics. Then first of all we discuss on the definition of the statistical mechanics or statistical physics. That is what the branch of physics which deals with the study of the collective behavior of the system of many particles. We are studying the collective behavior of the system and with the help of the principle of statistics, and therefore this mechanics is called as the statistical mechanics. This is our syllabus of the topic, and this is a very important table regarding the difference between the classical and quantum statistics. First of all, I mention here the classical statistics. Classical statistics is also known as the Maxwell-Boltzmann statistics. Remember that this is the name of the scientist, Maxwell and Boltzmann. Maxwell-Boltzmann statistics, in which we classify our particles on the basis of their property, that the particles are identical but they are distinguishable. The particles are distinguishable. How? Due to the wide energy level or wide band gap of energy, we distinguish the particles, and therefore in Maxwell-Boltzmann distribution, or you can say that in classical statistics, particles are identical but they are distinguishable, and they have no integral spin. Okay, and means they are not follow the Pauli's exclusion principle. What is the Pauli's exclusion principle? Pauli's exclusion principle is mentioned for these two four quantum numbers, n, l, ml and ms, and the classical particle does not obey the Pauli's exclusion principle. This is very important thing. In Maxwell-Boltzmann distribution law, particles are identical and distinguishable. Why they are distinguishable? Because they are widely distributed, wide band gap energy is there, and therefore they are distributed widely. Therefore they are distinguishable, identical and distinguishable. While we are considering about the quantum statistics, in quantum statistics there are the two types. What are that? There are the two types are Bose-Einstein statistics and Fermi-Dirac statistics. Bose-Einstein statistics and Fermi-Dirac statistics, and how they are distinguishable? First of all, in Bose-Einstein statistics, particles are identical, indistinguishable, but the consideration of the spin is important. In the Bose-Einstein statistics, we consider that particle has the integral spin. Particle has integral spin, that is 0 or 1, or integral multiple 0, 1, 2, 3, 4, like that. We are consider that it has the 0 or integral spin. Remember that it is not follow, means particle does not follow the Pauli's exclusion principle, and these are the important that the particle in Maxwell-Boltzmann statistics are known as the air. Okay, remember that air particle or molecule of the gas, while in Bose-Einstein statistics, the particles are identical, indistinguishable, and do not obey the Pauli's exclusion principle, means no two or more particle having these four quantum numbers.
What are these four quantum numbers? N means principal quantum number, L is the orbital quantum number, Ml is the magnetic orbital quantum number, Ms is the magnetic spin quantum number. Means if we are considering the two particles, they never have the same four quantum numbers. Means one of the quantum numbers may be changed. One of the quantum number may be changed. These four set of quantum numbers never same for the two particles, but in Bose-Einstein it may be possible. It may be possible that two particles have the same, because they are not following the Pauli's exclusion principle. Pauli's exclusion principle states that no two particles have these four quantum numbers, but we are not following, we are not obeying, therefore it may be possible particle has the four quantum numbers may be same. Okay, particle has the integral spin like this 0, 1, 2, 3, 4, 5, 6, and the particles which are belongs to or obeys the follows the Bose-Einstein statistics are known as the bosons, while the particle is known as the classical particle in Maxwell-Boltzmann, because already we considered that Maxwell-Boltzmann distribution is the classical statistics, therefore the particle obeys that as the classical particles. And the last one, that is the Fermi-Dirac statistics. Fermi-Dirac statistics. Remember that these three are different statistics, but we are considering the Maxwell-Boltzmann as the classical statistics, while for quantum statistics we consider the Bose-Einstein and Fermi-Dirac. Then what is the difference between the Bose-Einstein and Fermi-Dirac? That is what particles are identical, particles are indistinguishable. Why? Because the closely packed energy levels. Energy levels are very close, therefore we are considering that the particles are indistinguishable. Okay, but they obey the Pauli's exclusion principle. Means particle obeys the Pauli's exclusion principle. Means what? No two particles have same quantum numbers. See, they are not obey Pauli's exclusion principle, not obey the Pauli's exclusion principle. These also not obey the Pauli's exclusion principle, but they obey the Pauli's exclusion principle. It means what? Any two particles have these four quantum numbers. Okay, and generally the spin of these particle numbers are half, 1 by 2, 3 by 2, 5 by 2, like that one, and the particles are known as the fermions. Particles are known as the fermions. Remember that for Maxwell-Boltzmann distribution law, obeys the particle are known as the classical particle. For Bose-Einstein distribution follow particle, that particle are known as the bosons. And remember that one of the scientists is there, Bose, S.N. Bose, Satyendranath Bose. It is one of the Indian scientists. Remember that Satyendranath Bose is one of the scientists who will collaboratively work with the Einstein, and this distribution is known as the Bose-Einstein statistics. Higgs boson, one of the particle which is estimated or theoretically estimated about that by the S.N. Bose, and after that in last 5 years we get the existence of the Higgs bosons. Okay, now Fermi-Dirac statistics. In Fermi-Dirac statistics, particles are identical, indistinguishable, and obey the Pauli's exclusion principle. Also have the half spin, integral multiple of half spin. Here 0, 1, 2, 3. Here is a half, 1 half, 3 by 2, 5 by 2, 7 by 2, like that one, half integral spin. Okay, an example of Bose-Einstein's particle is photons, like this. Photons are the particles which obey the Bose-Einstein statistics, while in Fermi-Dirac statistics the example are the electron, proton, neutron, like these particles are there. Not electron, it is a proton, neutron, like these particles are there. So it also we discuss the distribution of the particle. We can represent the inner states or distribution function which is equal to a e raised to minus alpha by kt for the Maxwell-Boltzmann distribution law, and similarly for Bose-Einstein it comes like a e raised to alpha, e raised to beta e raised to epsilon by kt minus 1, and for this there is a plus and there is a minus. Remember that there is the only difference is that here is a plus 1 minus 1. This is the distribution function. We can represent the number of particles in each state, and number of particles are more in the Maxwell-Boltzmann distribution law. With this, I am concluding this difference between the classical statistics and quantum statistics. Thank you.